Dear friends, well, now you have your ideal vitrectomy machine, and before starting to operate, you have to make some choices and settings to meet your requirements, which are remove the vitreous efficiently, avoiding ocular hypotonia, ocular hypertonia, vitreoretinal incarceration, and bites or retinal tears. You must therefore choose which gauge you are going to work with, and according to this, which maximum aspiration flow, vacuum, and cutting frequency figures you are going to register in your different programs. So, of course, if the 3 previous chapters concerning the characteristic of the vitrectomy machine are based on universal physical laws of fluid dynamics, what I'm going to tell you now is based only on my experience and therefore involves only me. Well, I know that residents learn to operate detachment in 25G and will therefore find me very old-fashioned, even out of date, in my choices, since I have practically always operated the retinal detachment with 20 gauge without trocha, without any feeling of need to change. I don't want to convince you to cooperate without a trocha. I just want to explain to you the reason why I have been able to resist for so long to this irrepressible race for the smallest, the fastest, and finally the most expensive, a race in which the winner is not the patient but the industry. You have understood throughout these chapters that vitrectomy in retinal detachment does not have all the same goals and requirements as in macular surgery. In macular surgery, a part of the vitreous is removed only to allow the surgeon to work easily. There is no obligation to remove the entire vitreous, and the transconjunctival approach with trocha is probably a step forward. At least this is how I was operating the macula. In retinal detachment, in my vitrectomy indications, which are, with very rare exceptions, the same as those of the EVS-RD study, the clinical picture is serious enough to require a complete vitrectomy, and statistics have shown us that the removal of the posterior haloid and to perform it, the use of the high performance machine considerably reduce the risk of failure and the need to inject silicone oil. However, as we have seen previously, the performance of this complete vitrectomy with pinning of posterior haloid requires a retroequatorial scleral depression and therefore a conjunctival incision. Yes, the only detachment that can be operated by vitrectomy without conjunctival incision are, in 95% of cases, detachments for which there is no indication for vitrectomy. The remaining 5% are indication independent of the PVR stage, for example, the vitreous hemorrhage or capsular opacity. If you therefore admit that you need a scleral depression for your complete vitrectomy and therefore a conjunctival incision, then the usefulness of placing trocha will appear questionable. Because in the end, the main justification for trocha is to be able to find the sclerotomy through the conjunctival wall. This is why we place a trocha and accept that the whole driven by the trocha is much larger than the one we need for our handpiece. But since the main justification no longer exists when you have had a conjunctival incision, what other reason would be there for placing a trocha? The other reason would be to allow entry and exit with less risk of vitreal incarcerations. This is what I heard. To find out, let's ask those who can tell us whether it is true or not, the endoscopists. I questioned Jean-Paul Amar, Claude Baucher, and Alexandre Portman. They told me that the use of trochas does not lead to less incarceration, confirming what Frank Koch had said in earlier times. Two of them even claim that there is more incarceration because there is more vitreous left around the trochas, and have even returned to surgery without trocha when a complete vitrectomy is required, with or without endoscopy. So you see, confirmation has been given to us. When a conjunctival incision is performed, there is no reason to use a trocha, all the more since, truly speaking, a 23G trocha has a 20G scleral opening, and a 25G trocha has a 23G opening. I used to do a conjunctival incision every time I did a vitrectomy for retinal detachment. This explains why I was operating in 20G without trocha. So you can say, okay, but why not to operate in 23G without trocha, or even 25G without trocha? There are three reasons for this. Two of them are specific of 25G. On the one hand, the flexibility of the instruments. In macular surgery, the instruments are almost always vertical. There is no problem, there is no lateral pressure. In detachment, it is different, especially for peripheral vitrectomy, where the instrument can twist and become dangerous. On the other hand, as I have already told you in macular surgery, at the time I was operating, there were no 25G peak to initiate the peeling of an adherent hyaloid. However, in this case of detachment requiring a vitrectomy, the peeling of the hyaloid is essential. The third reason that is common to all gauge other than 20G is that there were not, and I believe there still is not, a 23 or 25G infusion kit such as the FCI kit in 20G. This kit includes, in addition to the kill plans that I already told you about, a calibrated knife with a stop to make a trapezoidal scleral incision. Why trapezoidal? Because not all instruments have the same diameter. Let me explain. If you use a lancet to make your sclerotomy, you will have an incision with parallel edges, wide enough to allow the handpiece to pass through, but too wide for the membrane forceps, whose body is thinner. There will therefore be some leakage. The FCI knives makes an incision that, at the scleral surface, is wide enough to allow easy insertion of the handpiece, but at the choroidal level is less than 20G, and therefore allow a seal also for the membrane forceps. The kit also includes a beveled infusion with a small projection giving its self-locking character. Once in place, the infusion cannot come out under the effect of an involuntary maneuver or under the effect of the pressure of silicone injection, as this is the case for the usual trocha. This reduces the risk of infusion under the retina. There is no doubt that if such a kit had existed in 23G, I would have worked in 23G. In 25 perhaps not because of the flexibility of the instrument, but in 23, yes. Well, you have chosen the gauges you are going to work with. Now you have to set up your machine in terms of infusion, maximum vacuum, maximum aspiration flow, and cutting frequency. First of all, the infusion. The setting of your infusion will condition two things: the infusion pressure and the infusion rate. The infusion pressure is the only thing responsible for the intraocular pressure, whether it is related to the height of the dropper of a bottle in a gravity system or to the pressure you have had pre-selected in an IOP system. It is the same. And this, whatever the internal diameter of the tubing you have chosen, 20G, 23G, 25G, or 27G. This is the same. When you are not aspirating, that is to say, when your pump does not create an aspiration flow, the infusion pressure will be the same throughout the eye, the infusion tubing, and the aspirating tubing. The only time this is not true is when the infusion line is clamped. This is why it is so important to have the infusion control on the foot pedal so that you can stop the infusion every time you remove an instrument to prevent the infusion pressure from pushing your vitreous into the sclerotomies, even if you have a valve trochas. When you aspirate, the pump creates a gradient of pressure and lower a little bit the intraocular pressure. With a gravity system and a dropper 60 centimeters above the patient's eye, if you create an aspiration flow of 6 or 7 cc's per minute, which is already quite good, almost twice the volume of the globe, in 1 minute, the intraocular pressure will go from 46 to 40, which frankly, it's not really a problem. As soon as you don't aspirate anymore, it will go back up to 46 millimeters of mercury. Never more, never less, unless you pinch the infusion tubing or clamp it. In the IOP system, the machine compensates for this pressure loss as you can do by lifting the infusion bottle. On the other hand, each time you stop the aspiration, the intraocular pressure will undergo a shock wave due to the inertia of the system. This is why I use gravity. I also liked to have a slightly firm eye to avoid focus variation due to hypotonia. That's why I like to have an IOP around 40 millimeters of mercury and therefore place the dropper 60 centimeters above the patient's eye, which itself must be placed at the same height as the pump of your machine. Otherwise, all the figures will be distorted. Check this detail. It is important. The infusion rate now depends on the infusion pressure, but also on the internal diameter of the infusion tubing and of the infusion line. You must therefore know the maximum infusion flow rate of the system you have chosen, because it will condition your maximum aspiration flow rate to avoid aspiration more than your infusion capacity, which would lead to severe hypotonia. I would like to draw your attention to a problem. The smaller the diameter you work with, in 25G or even more in 27G, the lower your maximum infusion rate will be. For example, in 27G with the normal infusion line, your maximum infusion rate is about 6 cc minute. If, like me, you don't like to work on a soft eye, you won't be able to aspirate more than 4 cc minute, which for your central vitrectomy may seem insufficient. You will then have two solutions. Either you use a high flow infusion line that raises your maximum flow rate at 10 cc per minute, and you can then aspirate at 6 or 7 or even 8 cc per minute. Or you may be tempted to increase the maximum infusion rate by lifting the battle or increasing the infusion parameter of the IOP system. But then be careful, because in order to restore an infusion flow rate at 10 cc per minute, that is to say, to increase your infusion by 60%, you will have to exert a 60% higher infusion pressure, which, when you stop your aspiration, will create a very high intraocular pressure with all the consequences that this implies. I therefore absolutely advise you to avoid compensating for the low infusion rate in 25 or 27G. Simply adapt your aspiration flow rate according to what your infusion flow rate can give you under normal conditions, although it may take a little more time. Now let's see the maximum vacuum. It will be fast. As you are in aspiration flow control, the vacuum that will be produced to obtain the required flow rate will be measured by the machine, but it will be done automatically according to the flow rate and the viscosity of the fluid. In my opinion, there is no reason to put on a limit of the vacuum. You don't limit the number of revolutions per minute of a car engine as long as you control the speed, because you may need a reserve of power in case of emergency to overtake a trunk. It is the same here. As long as you control the flow, why not use minus 600 millimeters of mercury or minus 650 millimeters of mercury when you are in a viscous vitreous? You leave, so please leave your vacuum at the maximum of what the machine offers. Now regarding the aspiration flow, if you don't mind, I will address it at the same time as the cutting frequency, because these two parameters work together. In general, the more you increase the aspiration flow, the more efficient you are, but the greater the risk of distant traction. The more you increase your cutting frequency, the less efficient you are, but the less risk you have of distant traction. The problem is that each detachment is different, depending on whether the vitreous has posterior adhesion or not, whether it is quite viscous or liquefied, whether the tear is very small or very large, whether the ciliary retina is detached or not, etc., etc., which makes that the aspiration flow rate and the cutting frequency must be controlled independently for each other and be adapted on a case-by-case basis according to the clinical specificities and the risk involved. So don't take the example of programs that I'm going to offer you as hyper safe. You must adapt your parameters to each particular case. You do not drive on a mountain road with the same parameters as on a motorway. That being said, here is a base of fairly logical programs you can work with. First, for centroid vitrectomy. When the retina and posterior crystalloid are far from where you work, you may reasonably want to be efficient, so you will choose a fairly high aspiration. If, like me, you like to work on a firm eye to avoid intraoperative hypotonia folds, your maximum aspiration will not come within 2 cc per minute of your maximum infusion. This will also go well with the desire to hear the vitreous speak, since you will be in areas where the vacuum required to obtain the flow in the vitreous is far from that in the BSS. To hear the sound of the vacuum varies to hear the sound of the vitreous. Be sure to set the sound according to the vacuum and not according to the flow rate, as I already told you. So you will choose in 20G a flow of 12 to 14 cc per minute, in 23G a flow of 10 cc per minute, in 25G a flow of 7 cc per minute, in 27G with high flow line a flow of 5 to 6 cc per minute, and in 27G normal line a flow of 4 cc per minute. As for the cutting frequency, if you want to be efficient, that is to say to have the time between 2 cuts to suck the neighboring vitreous, do not cut at more than 1200 cuts per minute. Personally, my maximum cutting frequency was 800 to 1000 cuts per minute. If you cut beyond 2000 cuts per minute or 2500 cuts per minute, you will only suck up the vitreous in contact with the door of your handpiece. To remove more vitreous, you will have to systematically sweat the 4000 cubic millimeters of vitreous, and you will not be efficient. On the other hand, when you use a good aspiration flow, especially in 20 or 23G, around 10 to 12 cc per minute, do not cut with a frequency too low, less than 300 cuts per minute, because there your vitreous attraction will be very strong and you can risk causing tear at a distance. For peripheral vitrectomy, when you are close to the retina or the posterior crystalloid, the challenge is no longer to be efficient but to be precise. Therefore, There is no longer the need to aspirate flow rate, to have aspiration flow rate higher than 5 cc's per minute or even 4 cc's per minute. With this limit, if you know how to have a light foot on the pedal, it will be very easy to lower your aspiration flow to less than 1 cc per minute. As for cutting frequency, my maximum was 600 cuts per minute or 10 cuts per second. Again, no problem to reduce this frequency to 1 cut per second or every 2 seconds. As for the vacuum, again, there is no point in limiting it. You may need this reserve during a posterior haloid peel when you will have engaged the haloid fibers in the port, making an occlusion, and then benefiting from the high power reserve up to minus 650 millimeters of mercury to peel the haloid plaque off. This is the advantage of working in flow control, because you can achieve this occlusion thanks to a session flow of 2 cc's per minute and raise the vacuum up to minus 650 millimeters of mercury without risk of problems, since at the rupture of occlusion you are still working at 2 cc's per minute and will no longer have the effect of the vacuum at minus 650 millimeters of mercury as in a venturi. So some of us find it difficult to manage at the same time the pressure of our foot on the pedal to decrease or increase the flow and the monitoring of the NPs. They tend to work with their feet on the ground a little bit. I can then advise them to do 3 programs, with a central program, a median peripheral program with a maximum flow of 6 cc per minute, and a peripheral program with a max flow of 3 cc's per minute. That's it. You have finished setting of your machine. You are now ready to start your vitrectomy. I have already said almost everything. I only have a few tips left, which will be seen in the next chapter. See you soon.